Okay, can you hear me? Okay, I have uploaded the exercise question on the Blackboard, so you may have a look and we may start to discuss the question 10 minutes later. Okay, so I think we may start now. So let me share my screen. Okay, can you see the screen? Okay, so let's discuss the first question. So for the first question, we are asked to find the number of meson combinations that we can make with this number of quark flavors. So just first explain some of the keywords in the question. So in the quark model, meson is composed of a quark and an antiquark, and quark flavor simply means the type of quark. So in standard model, we have 6 quark flavors: the up quark, down quark, charm quark, strange quark, top quark, and bottom quark. So we have 6 quark flavors. And so for the question, we can consider the simplest case first. So let's assume we have one flavor and assume that flavor is U. So the only possibility will be UU bar. So there's one meson combination when there's one flavor. And then we can consider 2 flavors. And in this case, we can write down UU bar, DD bar, UD bar, and DU bar. So there are 4 meson combinations. So up to now, we can observe some general rules. So we can consider the first quark, and we have, in the case of 2 flavors, we will have 2 choices for choosing this quark. And we also have 2 choices for choosing the anti-quarks. So in total, we have 2 times 2 equals to 4 combinations. And so it's quite straightforward to conclude that if we have n flavors, then there will be n times n equals to n square combinations. Okay, is there any question? Okay, why some mesons are UU plus DD? Okay, because in quantum mechanics we have superposition of states. Because in this question we are not considering that level, so we just simply say meson is quark plus antiquark. But in reality, we can have superposition. For example, as you said, pions is in fact UU bar, maybe, I don't remember, maybe plus or minus over square root 2. So it means that when we measure the pions, we will have 1/2 probability to measure them in UU bar states and 1/2 probability to measure them in DD bar states. So that's what's happening in reality. But in this question, we just don't consider superposition. Okay. Okay, so for the second question, is similar to question 1, but here we consider baryon combinations. So baryon simply composed of 3 quarks, and for anti-baryons, they consist of 3 anti-quarks, but we are not considering anti-baryon here. So we just have to consider the quarks. And similarly, we have 6 flavors in standard model, and we can start with the simplest case. So when there's only 1 flavor, the only possibility will be UUU. So there's only 1 baryon combination. And now let's consider 2 flavors, and we can decompose into 2 cases. The first case is that the 3 quarks are all the same. So we can write down UUU and DDD. And the second case is that 2 of the quarks are the same. So we can have UUD and UDD. So there will be 4 baryon combinations. And for the case of 3 flavors, we can decompose into 3 cases. So in the first case, the 3 quarks are all the same. So we can have UUU, DED, and CEC. And in the second case, only 2 of them are the same. So we have So we can write down these 6 possibilities. And for the last case, all the 3 quarks are different. So we can write down UDC. So in total, we have 10 baryon combinations if we have 3 flavors. And now we can generalize this into n flavors. And similarly, we can also decompose into these 3 cases. So in the first cases, if all the quarks are the same, then we will have n possibilities. And for the second case, we require 2 of them, only 2 of them are the same. And in this case, there will be n times n-1 possibilities. So the n refers to the number of how we choose the repeated quarks. So because there are n flavors, so we have n choices to choose the repeated quark. And the n-1 is the number of possibilities that we choose the remaining quark. Because when we have chosen 1 quark for the repeated quarks, then we only have n-1 choices for us to choose the remaining quark. Okay. And for the last case, when all the quarks are different, then it means we have to choose 3 different flavors out of the n flavors. So the number of possibility will be nc3, and it's equals to n-1 n-2 over 6. So in total, when we have n flavors, then we just add these 3 terms, and there will be the answer will be like this. So let's move to the next question. So in this question, we are asked to construct a table of all the possible baryons using these 4 quarks. And we also have to count the number of baryons which carry a charm of +1, +2, and +3. And just a reminder that charm is defined as the number of charm quark minus the number of anti-charm quark in the hard bonds. And also just a note, the strangeness definition is opposite, is the number of anti-strange quark minus the number of strange quarks. For example, for the kaons, it consists of U S bar, and according to this definition, it has a strangeness of 1. So these 2 definitions are opposite. So just a reminder. So to solve this question, we can first construct a table. And similarly, we can decompose into 3 cases. So for the first case, we consider all the 3 quarks are the same. So we have 4 possibilities. And for the second case, we consider 2 of them are the same. And the last case, of the quarks are different. So in total, there are 20 possibilities. And so we can find the baryon which carry only 1 charm quarks, and they will have a charm of +1. And similarly, we can find these 3, they will have the charm +2, and lastly, this baryon will have charm +3. So let's move on to the next question. So in this question, we are asked to determine the mass of the virtual photon in each of the lowest order diagrams for Baba scattering. And we use the assumption that the electron and positron are at rest. So Baba scattering simply means the scattering between electron and positron. And if you remember last time I said interaction is the exchange of particles, but more accurately, it should be exchange of virtual particles. For example, in electromagnetic interaction, it is mediated by virtual photon. So the word virtual just means that they are not real particles, because for real particles, we can detect them by our detectors, but for virtual particles, we cannot detect them. And so they can have different properties from the real particles. And we will see that in this question. So first, we can draw the diagrams for the scattering. So in geometric interaction, they only allow vertex. It's like this. So one lepton in and one lepton out and a photon. So this is the only allowed vertex. So if you draw something like this or this, then they are wrong. Okay, why this only allow vertex? Because for the other vertex, they will not conserve energy and momentum. For example, if you draw something like this, then it will refer to an electron in a photon. But if you consider the center of mass frame, the two electrons will have total momentum 0, but you cannot have, you can never have the photon of momentum 0. So they're not allowed because sometimes they violate energy and momentum conservation. And so the only allowed vertex is like this. Okay, let me think about that. Yes, for this vertex, they also not conserving charge. So Yeah, maybe I can check. Answer you later. I have to think about it. So we can just so let's draw the diagrams of the scattering. So we have an electron and positron. So the first possibility is to join them like this. So, and second possibility, is like this. So these two diagrams represent the same process, but the only difference is how they exchange the virtual photon. So we can first consider the first diagram. So, as the hint suggests, we can use conservation of energy and momentum. So I suppose you know for momentum. So we can assume the electron have full momentum P1, and because it's at rest, so the full momentum is just like this. And for the positron, assume the full momentum is P2, and because it's also at rest, so the full momentum is like this. And because for each vertex, the energy and momentum should conserve, and so the full momentum of this photon should be P1 plus P2. And so the energy of the photon will be just the rest energy of these two, of the electron and positron, and it will be 2mc squared. And also the momentum of the photon will be 0. And just to remind you that the relativistic energy and momentum is defined as gamma mc squared and gamma mv. And so we can conclude that the velocity will be 0 and the mass of the photon will be 2mv. So we can now consider this diagram, and similarly we can consider the full momentum. And by the assumption that they are at rest, so for the final state, the full momentum should also be like this. So if we consider energy momentum conservation in these two vertex, then the forward momentum of the photon will be 0. So the energy and the momentum of the photon will be 0. And so the velocity and the mass will also be 0. And so you can see that the virtual photons will have a properties that will be impossible for real photons. Because for real photons, we have mass equals 0 and the speed should be the speed of light. But they are not the case in virtual photons. Because in if you in the real process, for a vertex, if I said the only allowed vertex is one lepton in, one lepton out, and a photon. So although they do not have the properties of a real photons, we still call it a photon because the allowed vertex is like this. Just like in QCD, we have one quark and one gluon, and we will call it a virtual gluon, just because the allowed vertex is like this. Yes. So for the final question, we are asked to draw all the fourth order diagrams for quantum scattering. And fourth order just means there are 4 vertexes. So quantum scattering just means the scattering of electron and photon. So we can draw the 3-level diagrams first. So we have the 1 electron and 1 photon. So first we can join them like this. And second case, consider this. So now these two diagrams already have two vertices. So we now want to add two more vertices onto these diagrams. And there are two tricks. And the first trick is to consider the electron length. We can add two more vertex by adding a photon here. So we can see there are two more vertices. So we can consider adding the loop here. And we can also add in here. And we can also cross the two legs. So by this trick, we have 6 fourth order diagrams. And similarly, for this, we can also do this trick. So also have 6 diagrams here. And the second trick is to consider the photon length. So we can add an electron loop here. So there are two vertices here. So now we can have and also for this leg. So we have 2 more diagrams after using this trick. And similarly for this diagram. So now we have already drawn 16 diagrams. So we have 1 more diagram. And the last one is more tricky because it cannot be obtained by modifying the 3-level diagrams. and it's like this. So there's a electron loop here. So there are the 4 vertices are here. So this is the last diagram. So in total, we have 17 diagrams. Yeah, the last one is the most difficult, and I also don't know before looking up the answers. Yeah, so it's okay if you can't think about that. So yeah, you can just remember that there's also one special case here. Okay, and for the question that why the allowed vertex is like this, and I've looked up the slides in the lectures, and it said that this primitive vertex does not represent a possible process, and because as the student said, it will violate momentum. And yeah, but the slides do not explain why this is the only allowed vertex. So yeah, maybe I can search more and answer you next time. Yeah, the vertex does not represent a possible physical process. It's just a building block. Yeah, but this one is absolutely not allowed because it also violates charge conservation. Okay, so that's all, and you may leave if you have no question. No, momentum is always conserved because no matter, so for a vertex, they should conserve momentum, and for the whole process, it also should conserve the momentum. And is the reason that this vertex does not conserve momentum, and so it cannot be a physical process. In the midway in a process. See. So let me consider this. So this will not be a possible physical process because this is a real photon. So this will represent the process like this. And this is not allowed because it will conserve Faraday momentum. But in the middle, if you draw something like this, then it is allowed because this is not the real photons, but the virtual photon. So it can, so it is allowed. But for each vertex, they also conserve momentum.
Yeah, what I mean is, so overall the process is conserving momentum and charge and mass and everything. Yeah. But what I mean is, if you chop it in the middle and you said, because that one is a virtual photon, it's not an actual real photon, so the momentum need not to conserve. But then following the same argument, I could also say
the momentum is also conserved, and is because we want to conserve momentum, so we say this is not the real photon.
Yeah, that is not a real photon. That's why, I mean, if you hold on, let me turn on the annotate thing. I mean, if you consider only this frame, this little part, like at this time t, the momentum is not conserved, right?
At this time t.
Yes.
No, it's also conserved because because you cannot. So first, you cannot chop it into the middle because then it will represent a real photons because it's an external leg. Because external leg will represent a real photons, and all the things inside will be undetectable.
So yeah, it's undetectable, but the momentum is a physical quantity. It doesn't care if you can detect it or not, right?
Right. So let me see how to explain. Yes.
Yeah, now, but the
because
thing is,
we want to conserve momentum in each vertex, so that will make the photons a virtual photon.
So if the photon allowed to have zero momentum during a virtual photon, being a virtual photon allow it to have zero momentum, why can't it also possess charge? This is what I'm trying to say, because now if you say that real photon have to have some momentum, and then a virtual photon can suddenly have no momentum and it is allowed, then why can't I also have a photon that has some charge or some mass during a process, in the middle of a process being a virtual photon? And in that case, then the allowed vertexes will increase. You can have a I don't know, you can have a funny vertex in that case.
Okay. Okay, I have to say I also don't know because maybe I can search for you. But the fact that is that virtual photon can have zero momentum, and they can also have 3 spins, because real photons, they have 2 polarizations, but for virtual photons, they can have 3 spins, just like normal spin 1 particles.
Mm-hmm.
But charge,
and just now we also saw that the virtual photon can have mass. So
yeah,
now you say the virtual photon can have different spins, different momentum, different masses, then why can't it have different charges?
yeah, that's a good question. Okay, I'm searching. Okay, I cannot find an answer, because but I would say, so I would guess it is just a requirement, because although we call it a virtual photon, but we don't want because then it can be any particles. Then we will not call it a virtual photons. So we want to keep the photon properties as much as possible. I would that's my guess. So
They literally lose all property of a photon except the charge.
so because if we relax all the properties, then there's no reason to call them a virtual photon, right? It can be anything.
But gluon doesn't have a charge as well.
Yeah, but
And
it has
you allow
it has
the
color. Gluon has color.
So you're saying virtual photon and virtual gluon also can have different masses, different momentum, different spins. And the only difference between a virtual photon and virtual gluon is that one has color and the other one doesn't, and both of them has zero charge.
Yeah. You interact with virtual. Yeah, that may be an answer because in geometric interaction we cannot so we cannot have something like this. So this is not allowed. But in QCD, the gluons can interact each other. So that's
but those are the real photon and real gluons. We are talking about virtual photon and virtual gluon. It seems that in the world of virtual particle, everything is possible, and it's up to this point. It seems so.
Yeah, I would say that virtual doesn't mean that then no requirements. I would say that there should be still some similarity between a virtual photons and a real photons, such as the charge, the color, and we only allow them to have masses. I would say it like this.
Okay. Yeah. Okay.
Okay. Is there any question? Yeah, there may be some explanation in quantum field theory, but I'm also not an expert. Okay, so if there's no question, then we may end the meeting. Okay, goodbye.